Hi, so we are going to take a second pass over the max flow algorithm, and this time we're going to get it right. So previously we see that our version, first version of the max flow algorithm has a little problem, right? And the problem with a greedy algorithm like this, like the one we just looked at, is that it only looks for a locally optimal solution, right? So in our version of the Ford-Fulkerson algorithm, that is, we always try to send the largest possible flow for a given path, right? But as we see, that is a necessary part of the globally optimal solution, right? So we saw an example of how that does not give us the max flow. So what that means for greedy algorithms is that they in general kind of need some way to kind of backtrack or undo a locally optimal solution if and when necessary, so that it can eventually result in a globally optimal solution. Now, in the specific case of the max flow problem, it means that we actually, in order to figure out how to backtrack or undo, we have to look at kind of we have to understand the complete meaning of residual capacity. And before we can get there, we have to understand something called the flow cancellation or net flow. Both of these concepts are fairly intuitive, although they do lead to something that is slightly less intuitive. Anyway, so flow cancellation. Flow cancellation just means flow going between the same pair of vertices, but they go in opposite direction. They can cancel each other, right? So for example, here between A and B, there are two edges. They're opposite, right? One going from A to B, the other going from B to A. And they have different capacity, but that's not what we care about. What we care about in this case is there's a flow of two going from A to B, and there's a flow of two going from B to A. And they basically cancel each other. That means we are really sending nothing between them. So intuitively, in a real world example, if we say, send 2 gallons of water from A to B, and then we bring those 2 gallons of water back from B to A, then effectively we're not sending anything between those two vertices. So that's flow cancellation. So the next thing we'll talk about is net flow, which is really similar to flow cancellation. And it basically says between the same pair of vertices, and if they're flows in the opposite directions, but they're not exactly the same as each other, then instead of completely canceling each other out, it results in a net flow. Net flow is really just the difference between the two opposite flows. Right, so back to this same example here, but now we have a flow of 3 from A to B and a flow of 2 from B to A, then that results in a net flow of just 1 from vertex A to B, right? Another way to look at it, or a little more mathematical way of looking at this, is that the flow of 2 from B to A, that is the same as a flow of -2 going from A to B, right? That is by scale symmetry. So now we have a -2 flow plus a 3 flow, and you add 3 to -2, that results in a net flow of 1 going from A to B. So with these two concepts in our arsenal, we can look at the meaning of residual capacity again. So previously we said residual capacity is really just capacity minus flow. Now, and it reduced the residual capacity in the direction that the flow is sent in. But as it turns out, that's not all that is changed when the flow is sent through an edge. So to see that, let's consider the effect of sending a flow on residual capacity in both directions. So this is an example of, there is a residual capacity of 5 going from A to B. Now, this is exactly the same as this network with an additional edge with capacity of 0 going back from B to A, right? So nothing changed here. I mean, even though we added this edge, but we cannot send anything from B to A. So same as the original network, we cannot send anything from B to A. Next, let's try sending a flow of 3 from A to B. Now, by skew symmetry, we know that this flow of 3 from A to B is the same as a flow of -3 from B to A. So we actually added residual capacities going from B to A when we send a flow from A to B, which means not only we're reducing the edge from A to B by that flow, so the residual flow of that edge is now 2, which is 5 minus 3. Not only the residual capacity is reduced in this direction, but there is something that happened to the residual capacity going the other direction. And if you remember, by our formula, that residual capacity is just the capacity minus flow. Now the capacity is 0 and the flow is -3. So now we actually have a residual capacity of 0 minus -3 equal to 3 going from B to A. What that means intuitively is now we can send a flow of 1, 2, or 3 from B to A without violating the capacity constraint in this direction of the original graph. So let me say this again, maybe slightly differently if that helps, is that by sending a flow of 3 from A to B, we now can send a flow of at most 3 from B to A. And if we do that, then the net flow from B to A is still 0. And that is allowed by the original graph, right? Now, we obviously cannot send anything more than 3 in this direction because, say, if we send a flow of 4 from B to A, then we are sending, even though there is a flow of 3 from A to B, we're still sending a net flow of 1 from B to A, and that is not allowed by the original graph. But it's okay to send something to send a flow that's up to and including 3. So with this newfound understanding of how the residual capacity changes when we send a flow through the network, then we can now present the full Ford-Fulkerson algorithm. And so once we send a flow through a path, not only we're reducing the capacity of all the edges on that path, but we are also increasing the residual capacity of all the edges in the path in the reverse direction. Okay, so let's see how that fixes our example. So if you remember in our previous demonstration where the Ford-Fulkerson fail is we pick a path, we pick this path through the network and we send a flow of 3 through the network. Now we have to calculate the residual capacities. So previously, we only reduced the residual capacity in the forward direction, right? So those become 0, and this becomes 2, and this is becoming 0. Now, we also increase the residual capacity of all the edges in the opposite direction. Okay, so now since we send a flow of 3 on this edge, we're adding the residual capacity of 3 in the opposite edge. And then again, add the residual capacity of 3 in the opposite edge and add the residual capacity of 3 in the opposite edge. Now, given this new residual capacity network, we can actually find another path through it. And that is, we can go with this path now. And the maximum flow that can go through this path is 2. So we're sending a flow of 2, and flow of 2. And I just want to point out that now between B and C, well, there's a flow of 3 from B to C and a flow of 2 from C to B, which means there is a net flow of 1 going from B to C. And we know that flow of 1 is in the optimal max flow of this network. So if you remember, in the previous step, the algorithm has greedily sent a flow of 3 through this edge, but we know that's not optimal. And it is the added residual capacity in the opposite direction that gives the algorithm a chance to kind of partially backtrack or undo a suboptimal choice that it made earlier in this algorithm. Now, with this flow, we have to update all the residual capacities. And again, in the forward direction, we're reducing the residual capacity. So this, a flow of 2 over capacity of 2, the resulting residual capacity is 0. Going this way is 3 minus 2, that's 1. And going this way is 2 minus 2, and that results in 0. Now, again, we have to increase the residual capacity by the flow in the opposite direction. Okay, so that's why there is now a new capacity, a new edge with capacity of 2 going this way. Now, going this way, we are adding a capacity of 2 to the existing capacity, right? So 2 plus 2, that's why it's 4 now. And then finally, we create another edge with capacity of 2 going this way. Right, so given the updated residual capacities, we'll try to find another path through this network from A to D. It's probably a little hard to see. It probably helps that if we actually remove all the edges with the residual capacity of 0, we can no longer find a path from A to D in this network, which means we are done. And this would be the max flow from A to D in this graph. Now, if you look at this, it's very similar to what we had before, that the max flow is going out from A is 3 plus 2, and going into the sink is 2 plus 3, and so the max flow is 5. It's slightly different from what we had before because previously in the algorithm there is a net flow of 1 here, but if you look at what's going between B and C now, it's 3 going one way, 2 going the other way. So by the concept of net flow, it's the same as a net flow of going from B to C. Okay, so I hope that makes sense. If not, go back and look at the whole explanation again. But anyway, if you think you understand it, then you should again try this complete algorithm now through the same network. But as we did last time, that you should pick the path SADT first, which did not give you the max flow previously, but now run through this complete Ford-Fulkerson algorithm and see that it will eventually lead you to the max flow that looks like this. So now that we've demonstrated that Ford-Fulkerson works in our two examples, the question remains, does it work for all graphs? And when we talk about the correctness of an algorithm, typically we mean two things. One is the algorithm should finish at some point, right? It should not run forever. And the second thing is that it yields the solution that it returned is the optimal solution. So in case of the max flow problem, we want to make sure, the flow that it returns is the maximum flow. And if you think about Ford-Fulkerson carefully, it might not be immediately obvious that it meets these two conditions. Because first thing is, when we send a flow through the network, we're adding reverse edges, and and as a result, we keep creating additional capacities. Then, wouldn't we just then keep finding new paths so that the algorithm might never terminate, right? And then the second thing is the flow we add can go in the forward direction or the opposite direction. And for flows that go in opposite directions, it actually reduces the overall net flow. So how is it guaranteed that when the algorithm does terminate, that the flow we find is the maximum, right? So those are really interesting questions. And as a matter of fact, that it can be proved that Ford-Fulkerson is correct. And for it to terminate, it can be proved that if we use breadth first search to pick our path with available capacity, then it will always terminate. And that is actually a very simple variant, using BFS to pick out a path. That is a very simple variant on Ford-Fulkerson, and it actually has a name for it because it's discovered by Edmond and Karp. So that guarantees the termination, and then it can be proved that when it terminates, then it finds the maximum flow. Now the proof of that is very long. I found the proof, a fairly readable proof, in my algorithm textbook, but it's over 10 pages long. So I'm not going to talk about it here. If you're interested, you might be able to find it on the internet or ask me, and I'll make a copy of my book for you or the relevant pages. But obviously, that is not required. What is required is that now that you have an understanding of how this algorithm works, you will be asked to implement that in your assignment. So this is your last assignment, and it's actually both the Java and the C++ version of 3C. They also implement the same thing, but obviously in their own language. And it is for the classes is the longest and the most complex assignment. Although I think with Python it's quite a bit easier. So anyway, so in the assignment I specified the interfaces uh, for the input. The input is basically how we specify the graph, the edge and the vertices, and then the output. I also has a specification for it. They are very similar to the graph and the Dijkstra implementation that we talked about earlier. So anyway, so it's highly recommended that you would start with the graph implementation, the Dijkstra implementation that I presented in the earlier videos, but it's up to you whether you want to do that. So only the interfaces are specified. The internal implementation, that's entirely up to you. And one last thing I want to say about is I've seen this done before and hope that it doesn't happen again, is that, don't just find the detailed line by line pseudocode on the internet and you just kind of implement it verbatim, but you don't understand how it actually works. Please do understand how it works, which again I already explained. So hopefully that already makes sense. But and then your implementation is based on your own understanding of the algorithm.